All right, here we are with AP Physics Work Kinetic Energy Theorem 2, problem 4. A 6,000 kilogram freight car rolls along rails with negligible friction. The car is brought to rest by a combination of two coiled springs. Both springs obey Hooke's law. There's our spring constants. After the first spring compresses a spring 30 centimeters, the second spring then comes into contact with the freight car, and now both springs are being crushed through an additional 20 centimeters, bringing the car to rest. Find the car's initial speed. So I'm going to start with my sketch. All right. Sketches are really important for energy problems, as you will see as we continue further. Okay, this is problem 4. So I have my freight car rolling along, going with an initial velocity of 1.5 meters per second. Okay, down the rails. And then it's going to hit some springs. Now, one spring is this all right, this kind of lightweight spring, all right, that they tell us that it has a spring constant of spring 1, we say K1, all right, that's lowercase k, K1, spring constant, is 1,600 newtons per meter. And it's going to hit this big, heavy spring, okay, this second spring, all right? It's going to crush this one 30 centimeters, and then it hits this big, heavy spring, right? Okay. And this big, heavy spring has a spring constant, lowercase k, spring constant, K2 of 3,400, all right, newtons per meter. Okay, and here's what we're going to do. It's going to crush this first spring down a distance of 30 centimeters. That's 0.30 meters. Then it contacts the second spring, and it's going to crush both of them down another 20 centimeters. That's 0.20 meters. And then when it gets to here, at that point, that's when the final velocity is going to be 0. So our initial velocity here, 1.5, our final velocity 0. It comes to rest there. With that information, we are supposed to determine what? I'm sorry. This was from a different problem. We want to find what was that starting velocity. All right, there we go. Sorry. So it's rolling along with some initial velocity we're trying to find, and it slams into these, dunk, and then chunk, and then gets brought here. What was that starting velocity? That's better. Okay, there we go. Makes sense. All right, so we are doing an energy problem. And really, we want to know the speed just before it hits. So our starting point is going to be here, right? And our ending point is going to be here. So we're analyzing the motion from here to here, starting with our great big energy formula, our work kinetic energy theorem, sigma W equals delta K. I'm going to go ahead and I'm going to put a work term in for every force acting on that. Now, we know that while we go from here to here, right, we could do a force diagram for that railroad car. Simplified one's going to look like this. There'll be a gravitational force. There'll be a normal force. Why did I write that FG instead of MG? I'm spending too much time with first-year students. Anyway, and then there's going to be a force from spring 1. And then later on, there'll be a force, right, from spring 2. Right? That's aggravating. I think I'm just going to call them F subscript 1 and F subscript 2. Is that okay? All right, thanks. Okay, and those are going to be going against the motion. They'll be slowing it down, bringing it to a stop. So as I look at this, while I move along this way, right, and you know we're going to do coordinate axes. First axis goes along the motion. Next one goes perpendicular to the motion, right? Let's call to the right positive. You know that those are the only forces in the parallel axis. You know they're going nice and parallel to the motion. This is going to be an easy calculation. Sure it is. So running through, we say there's going to be technically there'd be work by gravity plus work by normal plus work by spring 1 plus the work by spring 2 are going to equal delta K. That'd be the final kinetic energy minus the initial kinetic energy. These are capital Ks, the kinetic energy terms. Now, some of these will be 0. And I can just by inspection, I know that this normal force and gravitational, they are perpendicular to the motion. They have no component parallel to the motion. That means if I did punch in and do my dot product, my cosine theta for these guys, they'll be 90 degrees. Cosine of 90 degrees, that's the angle between the force and the motion, angle between that force and the motion. Cosine of 90 is 0. They're not doing any work. They're not helping it push faster or push slower. They're perpendicular to the motion. So I can just go whoop, whoop, right? This is because that gravitational force is perpendicular to the motion. And because that normal force is perpendicular to the motion, we're going to get zeros out when we evaluate those cosines, those cosine of 90s. So I really just have these two work terms. Now wait, it gets even simpler because the final velocity is 0. So when I punch in and do 1/2 mv squared, I'll do 1/2 m times 0 squared. This term is going to be 0 because v final is 0. All right. So I really am just going to have 3 terms. That's nice. That's nice. So let's figure out the work done by that first spring. So I'm going to do my integral of the force of spring 1 dot dx plus my integral, the force of spring 2 dot dx. And that'll equal minus the initial kinetic energy. What the heck? Let's go ahead and do a 1/2 K. Whoa, what am I doing? 1/2 mv squared. Oh my gosh. 1/2. Whew. Sorry about that. 1/2 mv naught squared. Oh my gosh. Kinetic energy. Kinetic energy. Thinking about the springs. Okay, anyway, here we go. Taking a look at these. Can I simplify these down into just the F dot delta X equation? And you say, no. Because while we crush this spring, the force from the spring is changing all the time. So this is not a constant force. So we're going to have to do the integral form. Okay, we cannot do the simplified version from last year. Sorry. However, let's run through this. It's not so bad. I know that my angle here, this is going to be a cosine of, what's the angle between the way the spring 1 is pushing and the way we're moving? That's 180 degrees. Same thing here for spring 2. It's pushing opposite the motion. That's just going to be -1, -1. That's nice. I'm going to get negative work terms here. Oh, look, I'm going to have minus a kinetic energy. I'm going to have negative on this side, going to have negative on this side. Going to work out perfectly. That's what we want to see. Okay. There is something really important, and this is the tricky part of this problem, and that is the bounds for my integral. All right. Let me address that. We are looking at this as we change position from x equals what to x equals what. So there is a tendency to go ahead and take a coordinate axis, and we're going to drop down, and we do something. There's a tendency for people to want to do this. Hey, let's call here on the sketch, let's call this x equals 0, and then let's just make our coordinate axis like this. And so we'll say, okay, this is going to go from 0 to 0.3, and then here's 0.2. And you're like, okay, this first spring, it's going to get crushed from x is 0 to x is 0.5. You know what I'm saying? 0 to 0.5. All right, does that make sense? Because the first spring continues getting crushed while it's crushing the second spring. And that's fine. But then when we get over here, people want to say, oh, this is from x is 0.3 to x is 0.5, right? You know what I'm saying? But that's not right. Because remember, the x in this equation now, and when we're dealing with a spring, in the force equation that we're going to plug in, these are ideal springs. So I'm going to plug in, kind of got to look ahead a step here, sorry. I'm going to be plugging in, force is, negative kx, right? This is k1x. And then cosine of 180 is going to be a -1, right? And then dx, absolute value, right? You know what I'm saying? 0 to 0.5. Same thing here. Negative, now it's the second spring constant, because the second spring, absolute value. And then a -1 from that cosine 180. And then dx. Okay, But the point is, these bounds, be careful. Remember, we're trying to make this x and this x be the same variable, right? And that's kind of okay because the distance we crush and the distance we move along, right? If I move along 20 centimeters, I crush the spring 20 centimeters, right? But remember, this x is the stretch or crush of the spring. This spring just started getting crushed here. This right here is x equals 0 for the second spring. That's the point where the force would be 0 for that spring. So that's when negative kx would be 0. You see what I'm saying? So this spring's bounds are not 0.3 to 0.5. This spring's bounds are 0 to 0.2. Do you see what I'm saying? That big spring is just getting crushed 20 centimeters. Remember, this x is the crush or stretch length, not just along a position axis. Right? I know it's weird, but that's what's going on here. Does that make sense? I mean, otherwise, you would say, hey, if I called this 0.3, that would mean right at the start, the spring was already pushing with a bunch of force. You know what I'm saying? The spring constant times 0.3 would be the force at when it hasn't even been crushed yet. That doesn't make sense. It's got to start from 0 force and build up. Okay, so that's the deal. That is the tricky part, okay? That is the tricky part of this problem, I would say. The x in that force equation for the spring is the stretch or crush distance. Okay, and that spring just started getting crushed there. Okay, moving onward. I feel like I've belabored that point sufficiently. Let's move along. Let's do our calculations now. Hey, looking at this, you recognize that I can do this integral. I'm taking absolute value of this. And all my x's, my x positions here, they're all positives, right? My crush, this is positive direction, right? So I'm taking absolute value of this. I can just get rid of that negative sign and make this thing positive because k is positive and x is positive. And the only negative here is going to be from this, and that's what I want. I want to get a negative answer. I should be getting negative work. So I'm just going to integrate negative. This negative is from this, not from this. Okay, negative kx dx. Okay, and you say, so I'm going to say, hey, what is k is a constant, x there. If I take an integral, I'm doing a derivative in reverse. This would have been like a 1/2 x squared, and then times a k. 1/2 k1 x squared. Evaluated from 0 to 5. Over here, same thing happens. This is going to be taking the integral of negative k2x dx. Right? This negative is the negative from this. This negative disappeared when I took the absolute value. Okay, this is that orange. I should have just kept it orange. Sorry. From 0 to 0.2. Integrating that, again, this is a constant. This negative k2 is a constant. So it's just the integral of x dx is going to be 1/2 x squared times negative k2. So negative 1/2 k2 x squared. Evaluated from 0 to 0.2. All right. Minus 1/2 mv naught squared. Okay. Track that down. Okay. Put in the values I know. You're like, okay, K1, that's going to be 1600, right? Yep. And then put in the 5 for the x, and then put in the minus when I put a 0. When I put a 0 in, it's just going to drop out. So it's just going to be 5 for the x, that's going to be times 25. Okay. Coming over here, I'm going to have a minus 1/2 times 3400 is my second spring constant. X squared, that's going to be a 0.2 squared. Oh my gosh, that's a 0.5 squared, isn't it? Sorry. Yeah, that's a 0.5. 0.5 squared would be 0.25. Sorry. There we go. Times 0.2 squared, that'll be 0.04. Okay. That's going to be equal to minus 1/2. What's the mass of this freight car anyway? They tell us it's a 6,000 kilogram freight car. That's V naught squared. There we go. There's my equation with just one variable, V naught. Right away, I see there's a negative in every term. there's a half in every term, so I can kind of just drop those right now, just divide through by -1/2. That'll make my life easier. In fact, if I wanted to, I could also divide by 100 every term, get rid of 2 of those zeros, right? I don't know if that makes a big difference for punching in my calculator, but you get the idea. I can simplify this down quite a bit. And so now I'm going to have 0.25 times 16, that's 4, right? And I'm going to have 0.04 times 34. All right, fine. Okay, divide by 60. And then I'm going to take a square root. And I get that my initial velocity was 0.29888 meters per second. Let's just round that off and say it was 0.299 meters per second was V naught. Ta-da! All right. Okay. That's problem 4. Okay. So again, the tricky bit is with the bounds there. Recognizing that with springs, that x is not just a position on a position axis, it's the crush length. So x equals 0 has to be where that crush is 0. It's going to happen at different spots for the different springs. So that's why my bounds look the way they do. Okay, that's problem 4.